in enthalpy. So I told you, if you remember, the word enthalpy always means it has got something to do with 1 mole. It is clear. How is electron gain enthalpy represented? This is delta electron gain H enthalpy. Delta EGH. How do you define electron gain enthalpy? It is the energy. It is the energy released. Generally, it is energy released. Two exceptions to the rule. When it is energy absorbed, that we will see. It is the, or I'll say it is the enthalpy change. So we are very sure. Enthalpy change can be what you call exothermic or endothermic. So what happens? We are on the safe side. It is the enthalpy change. It is the enthalpy change accompanying. It is the enthalpy change accompanying the accepting of 1 mole of electron, 1 mole of electron by an atom, in the gaseous state. By an atom in the gaseous state to form 1 mole of anion. Obviously, anion in the gaseous state, everything in the gaseous state. Anion in the gaseous state. Anion in the gaseous state. So you have 1 mole of a gaseous atom. It has accepted electron and it forms 1 mole of anion in the gaseous state. Okay. So when it forms a mono negative anion, so all electron gain involving formation of a mono-negatively charged ions are exothermic. Is this clear? This is the first point. So X this will be exothermic. So now look at this case. You have an anion, 1 mole of the anion now taking, here gaseous atom, it will be exothermic. Now anion taking an electron to form X minus 2. Now this will be endothermic. This will be endothermic. Why it will be endothermic? Because what happens is, already the anion has excess electrons. It is clear. Anion has excess electron. When you try to put more electrons in that, there is tremendous repulsion. And to overcome the repulsion, energy has to be supplied. So the net reaction, so in this case what happens? X to X minus 2. This may be exothermic, this may be endothermic. Net X plus 2 electrons forms X minus 2. This net reaction is endothermic. Net reaction is endothermic. There are two classic examples. Okay, we will give the correct values. There are two classic examples. Which are they? So we have, see, oxygen plus an electron forms O minus 2, also O minus 1, forms O minus 1. So for 1 mole this value is, so delta electron gain over here is minus 141 kilojoule per mole. Kilojoule per mole. But then this is a question which has been asked in the entrance exam. That's why I'm discussing that. So what happens is O minus the oxide ion to a di-negative anion plus 1 more mole to form O minus 2. Here the delta electron gain enthalpy was how much? It was 844 kilojoule per mole. Plus, it was plus. Plus means it is endothermic. 844 kilojoule per mole. So the net reaction O, oxygen atom in the gaseous state, plus 2 moles of electrons forms O minus 2. This net electron gain enthalpy will be how much? 844 plus 141 will be minus 141 will be how much? 844 minus 140 sorry, minus 141 will be, so this value will be plus 703 kilojoule per mole. This is one example. The other example is we have here, we can write over here, that is sulfur. Sulfur to S minus. So sulfur takes 1 mole of sulfur atom in the gaseous state takes 1 mole of electrons to form S minus in the gaseous state. This delta H value is how much? It is minus 200 kilojoule. This delta electron gain enthalpy is minus 200 kilojoule, it is kilojoule per mole. But look at the second situation. Sulfide the anion in the gaseous state accepts 1 more mole of electron to form S minus 2 gaseous. So in this case the value is around plus 532. So delta electron gain H is plus 532 kilojoule per mole. Plus 532 kilojoule per mole. So what is the net value? So net value is 332. So sulfur atom in the gaseous state taking 2 moles of electron to form S minus 2. This delta electron gain value will be plus 332 kilojoule per mole. So this is an exception. Normally when a gaseous atom accepts 1 mole of electron, that value will be always exothermic. These are two exceptions to the rule because these compounds are stable. Sulfur exists as S minus 2, oxygen exists as O minus 2. Therefore, we have to discuss this. Okay, in the stable state, their electron gain enthalpy is what you call endothermic. It is endothermic. 1 mole of gaseous atom accepted 1 mole of electron. What happens if one gaseous atom accepts 1 electron? It is clear. That will be called as electron affinity. So electron affinity, EA. Okay. So when one gaseous atom accepts an electron. So here is 1 mole accepting 1 mole of electron. Here one gaseous atom accepts 1 electron to form a gaseous anion. To form a gaseous anion is called as electron affinity. So understand the difference is called as electron affinity. So one gaseous atom accepts one electron to form one anion. Energy released, I am now using the word energy released because only two exceptional cases when it is exothermic, otherwise the energy released will always be what? Will be exothermic, energy will be released. Why is the energy released? The energy is released because what happens? The incoming electron faces repulsion. Is clear? So what is happening? Some amount of energy is released to overcome the repulsion. Is this clear? Now let us look at trends in a group. Trends in a group. When you look at trend in a group, what happens is, let us talk about lithium, sodium, potassium, rubidium, cesium, francium is not. Alkali metals generally form cations, they never form anions. So literally their delta electron gain enthalpy is nearly equal to 0. Is nearly equal to 0. But when we look at halogen, halogen is 17th group, okay. We have fluorine, chlorine, bromine, iodine and astatine. Astatine is again a radioactive element. What happens is, as we go down the group, so what are the points that we have to see? As we go down the group, you will agree with me that Z effective, that is effective nuclear charge increases. Effective nuclear charge increases. So what is going to happen? This will help. Now as we go in a period, effective nuclear charge decreases, sorry. So as we go down the group, effective nuclear charge is going to, what do you call? Yeah, effective nuclear charge increases. Effective nuclear charge decreases. And what happens? Atomic size increases. So this together, what is going to happen? The tendency to accept electron decreases. Tendency to accept electron decreases. Because an atomic size decreases, effective nuclear charge decreases. Atomic size increases, effective nuclear charge decreases. What is going to happen? The tendency, the nuclear pull on the outermost electron is going to become less. If the nuclear pull on the outermost electron becomes less, it like to lose the electron rather than gain electron. So tendency to gain electron decreases. Tendency to gain electron decreases. So electron gain enthalpy. Electron gain enthalpy decreases. Electron gain enthalpy decreases. So this might give you an idea, it might make you think that fluorine, which belongs to the second period, should have had the, what you call, maximum electron gain enthalpy. In fact, that also is a problem. It's an exception that elements of the second period, have electron gain enthalpy, less than elements of the third period. Elements of second period This is an anomalous behavior. That means we will have, see, look at group 13, boron, aluminium, gallium, indium. 14, let us say 14 is carbon, silicon, germanium, tin and lead. But more important, group 15 is nitrogen, phosphorus. Nitrogen will have less than phosphorus. Then group 16 is oxygen will have less than sulfur, and fluorine will have less than chlorine. Fluorine will have less than chlorine, main importance. So why is it so? The reason is because there's only one reason that we have to give. Why is it so? We have space here. Small atomic size. So elements of the second period have small atomic size. So incoming electron faces repulsion. Incoming electron faces repulsion. So some energy is used to overcome the repulsion. Some energy is used to overcome repulsion. So what is going to happen? The net energy release becomes less. Technically, the elements of the second period should have had more electron gain enthalpy, because we are saying it decreases in a group. So the first element in the group should have maximum. The first element does not have. So what does this finally tell you? What is the entrance exam question that we can have? This is the entrance exam question. What is it? That in the complete periodic table, now this is the entrance exam question, JEE NEET. What is it? That in the periodic table, what is happening? Chlorine has highest electron gain enthalpy. Minus 348 kilojoule per mole, I think. Yeah. It is delta is equal to minus 348 kilojoule per mole. So this is one question. It's not fluorine which has the highest electron gain enthalpy. It is chlorine. Fluorine has electron gain enthalpy less than that of chlorine. Explain. Give reason. Scientific reason. Only one. Fluorine has a very small atomic size. Incoming electron faces electron repulsion from the outermost. So some energy is used to stabilize. So fluorine has 7 electrons. It wants the 8th electron, but the already 7 which are there repelling. So it takes the 8, uses some energy to stabilize. So the net energy released is less. So that's why fluorine has electron gain enthalpy less than that of fluorine. So that results in what? Chlorine having the highest electron gain enthalpy. Then we come to what? In a period. So what happens in a period? So let us take lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So in a period, what is happening? In a period, first and foremost, what is happening? Effective nuclear charge increases. Effective nuclear charge increases. Why does it increase? Because electrons are getting added in the same shell. Atomic size decreases. Atomic size decreases. So, एक तो size is decreasing, nuclear becomes closer to the outermost electron. Effective nuclear charge is increasing. So, if nuclear charge is increasing, what happens? The incoming electron gets attracted very fast. So, in that case, what is happening? Incoming electron getting attracted or attached very fast is what? Electron gain enthalpy. So, electron gain enthalpy increases. So, electron gain enthalpy increases. So, automatically in whatever period that they are in, halogens have the highest electron gain enthalpy. In the period to which they belong, halogens have the highest electron gain enthalpy. But among halogens, chlorine has the highest electron gain enthalpy. So that results in what? That Chlorine is the one having maximum, what do you call, electron gain enthalpy in the complete periodic table. See, we are not discussing about transition element in it because they are metals. Metals are more electropositive. Their ionization enthalpy is a very important point for them. Electron gain, they do not form the anion. They are metals, they do not form anions. So we are not discussing much about their electron gain enthalpy. So that much time is saved. But we go to the next property. Okay. So when you go to the next property is the last one we are dealing with. The chapter gets over with this. The next is electronegativity. A lot of story has to be discussed over here. Electronegativity is given by the formula En. Okay. I mean, given by the words, not formula, given by the words En, electronegativity. Now you see, if you have a covalent bond being formed, if a single covalent bond is formed and the homonucleus, so it's a homonuclear single covalent bond, then what happens after the bond is formed? The pull of the nucleus towards this and the pull of the nucleus is going to be the same. But what happens is, if you have something like this HF, fluorine is able to pull the electron of hydrogen towards itself. So in a heteronuclear bond, in a heteronuclear bond, what happens? One of the atom tends to pull the electron, pull the bonded electron of the other towards itself. So that will lead to what? Slight polarity, delta negative and delta positive. So this tendency to pull the bonded pair of electron towards itself in a bond which it forms with the atom of another element is called as electronegativity. It is called as electronegativity. Now what happened was, Pauling studied this and assigned values En values. Okay. Mulliken also studied. So Mulliken, what he did, he said simply it is ionization potential plus electron gain enthalpy divided by 2, and this value was in electron volt. Is it clear? So, but everybody decided to follow Pauling scale. So we are following the Pauling scale. Is it clear? So what is electronegativity? It's the power of an atom. So what will you say? The definition is, it is the power of an atom. So definition is, it is the power of an atom to attract electron towards itself, to attract electrons towards itself in a bond which it forms with which it forms with atom of another element. Which it forms with atom of another element. Now, what is the use of this electronegativity value? Okay. See, the application of this is, then we are coming to the periodicity. The application is, we can find the percentage ionic character. See, if it is a perfect ionic bond, it's 100% ionic. Now, the electron was lost. But here this is a polar covalent bond. Na? This bond, this is a non-polar bond, whereas this will be a polar covalent bond. This will be a polar covalent bond. So what is going to happen in a polar covalent bond? Some amount of ionic characters introduced. How much is that? That calculation is asked. So percentage ionic character is given by the rule. It is 6 into XA minus XB plus 3.5 into XA minus XB the whole square, assuming that electronegativity of XA is greater than XB. So electronegativity of fluorine, 6 into fluorine minus hydrogen, that is 4 minus 2.1 plus 3.5 into 4 minus 2.1 the whole square. That will give you percentage ionic character. This is a question which they normally ask in entrance exam. Calculate the percentage ionic character. Okay. Now, according to Pauling, Pauling scale, fluorine is the most electronegative element. Fluorine is the most electronegative element. Fluorine is the most electronegative element in the periodic table. The periodic table, its value is equal to 4. So there is not going to be any element which has got a electronegativity greater than 4. 4 is the most electronegative element. Okay. Fluorine may not be having the most electron gain enthalpy, but fluorine is the most electronegative element. Okay. Then we look at the trend in property. So what is happening? Trend in a period or in a group. Let us take in a group. So in a group, what happens is, as we go down the group, the most electronegative elements happens to be group 17. That's what we are talking about. Literally, electronegativity will be 0 for what? For alkali metals, because they don't pull the electron. They are electropositive. They give electron. So 17 will be fluorine, chlorine, bromine, iodine. So value is 4. Then we have 3, 2.8 and 2.5 according to the Pauling scale. So this itself, half the story is told. What happens? As we go down the group, what is going to happen? Effective nuclear charge decreases, atomic size increases, so together, because of this, what is going to happen? The tendency of the atom becomes losing electron. So pulling somebody's electron becomes difficult. So electronegativity decreases. But there is a very interesting this. Now, as far as entrance exam is concerned, a lot of questions can be asked in this. Okay, what this is group 14. This is where the question is asked. Nobody, 11 they will ask the definition. But in the entrance exam they will ask exceptions. What is the exception? Group 14. Group 14 will be carbon, silicon, germanium, tin, lead. You will be surprised. Carbon has a value of 2.5 and all other fellows are having a value of 1.8. All others are having a value of 1.8. So imagine the order of the decreasing order of electronegativity of group 14 will be carbon greater than silicon equal to germanium equal to tin equal to lead. Do you think ever you will mark this answer? You will never mark, because you will always mark carbon less than silicon, less than germanium, less than tin, less than lead. But the fact is this is an exception. Then we have gallium. So that we are aluminium, gallium, indium. So now you see, we said that as we go down the group, now let us look at the ulta the opposite situation. What is it? That we said as we go down the group, electronegativity value decreases. So this is the first exception. Now we will come to the second exception. What happens in case of this group group 12 na 12 13 na in group 12, this is an exception. In group 12 you have zinc and then you have cadmium and then you have mercury. Zinc, cadmium, mercury. In case of zinc, cadmium, mercury, what is happening? 1.6, 1.7 and 1.9. So in which group does the electronegative value increase? It's odd behavior. This is how they are catching in entrance exam. Is this clear? Just the textbook says electronegativity decreases as we go down the group. That is exceptions is what we have to look at. So here group 12, that is zinc, cadmium, mercury, electronegative value increases as we go down the group. Exception, electronegativity value increases. So this is increases down the group. Increases down the group. Whereas division metals. Okay. Then we have group 13. Same problem with group 13. In group 13, what do we have? We have boron, aluminium, gallium, indium and thallium. So boron has the electronegativity value of 2. The next one, aluminium, what happens? It becomes 1.5. Good situation. It has decreased. But then after that, what happens? It increases 1.6, 1.7, 1.8. So you can imagine how the trend will be. The trend will be boron greater than thallium, greater than indium, greater than gallium and greater than aluminium. So now here is the question. If we say it decreases as we go down the group, and that one small thing we keep in the mind will get wrong. Why? Because if they ask a question in group 13 which has the least electronegativity, you will end up saying thallium. It is aluminium which has the least electronegativity. These are exceptions and which become questions in entrance exam. Okay. So this was in a group. Okay. Now let us look at the situation in a period. Now in a period, what happens in a period? Let us look at the second period. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Also the third period. Okay, what do we have? We have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. What happens? As we go down in a period, what happens? In a period, okay, first point is effective nuclear charge increases. Z effective, that is effective nuclear charge increases. Second, atomic size decreases. We never say nuclear pull increases. Nuclear pull is increasing, but always it is said in terms of effective nuclear charge, because that is the correct indication of this. So what is going to happen? Electronegativity increases. Electronegativity increases. So that makes what you call fluorine the most electronegative element in the complete periodic table. Is this clear? With this side, because there is a benchmark. So whenever the difference in the electronegativity is 2.3 or more, the oxide will be basic, and lower it will be. So whenever the difference in electronegativity is greater than 2.3, in an oxide, it is basic, and less than 2.3, the oxide is acidic. So if they give the electronegativity value of the oxide and ask what will be the nature of the oxide, simple. The nature of the oxide you can find out by the difference. Okay, so this is one more question. Now this was oxide, nature of hydroxide. So hydroxide we write as MOH. This M can be a metal or a non-metal. This M can be a metal or it can be a non-metal. Only difference is when it is a non-metal we call it as oxyacid. When it's a metal we call it as hydroxide. So here also there is a rule. What does the rule say? If M the value, okay, if M is greater than 1.7, this value for M, if it is greater than 1.7, the hydroxide will be acidic. The hydroxide will be acidic, and M less than 1.7, the hydroxide will be basic. The hydroxide will be basic. So this is one more aspect that we can see from point of view of what you call electronegativity. That is all. So actually with this we have completed periodicity of elements.